Hello everyone. In this video, we are going to discuss about electron gain enthalpy from the chapter 3 classification of elements and periodicity in properties class 11 chemistry. See, we have already discussed about the ionic radius, atomic radius and ionization enthalpy in our previous video, which will be available in the playlist. Now let us talk about electron gain enthalpy. See, when an electron is added to a neutral gaseous atom, see X is an atom, any atom which is a gaseous atom. So, when an electron is added to a neutral gaseous atom, to convert that atom into a negative ion, that is an anion, the enthalpy change accompanying the process that is actually defined as the electron gain enthalpy. See, electron gain enthalpy is actually represented like this, delta Eg, electron gain enthalpy, delta H, but subscript Eg is here, which represents electron gain enthalpy. See, enthalpy, that is actually a thermodynamic property. Enthalpy H, that is actually a thermodynamic property representing the total energy of the system. Now, change in enthalpy, that is delta H, that is a difference in enthalpy between the initial and final states of a system. And you see, electron gain enthalpy, that actually provides a measure of the ease with which an atom adds or gains an electron to form a negative ion or anion as represented by this equation. That is, here we have a gaseous atom X. It gains an electron so that it becomes a negative ion X minus. That is, for example, if you consider this case of chlorine, we are considering the chlorine in gaseous form. It gains one electron so that it becomes a chloride ion Cl minus ion. And the electron gain enthalpy in this process is minus 349 kilojoule per mole. See, the negative, here the electron gain enthalpy is negative. Negative electron gain enthalpy indicates that the energy is released during the electron addition. Okay, that is during this process, that is when an electron is added to the chlorine so that it becomes the chloride ion Cl minus ion, some energy is released during this electron addition. That is why we are having a negative sign here. See, if you consider the group 17 elements, halogens, they have very high negative electron gain enthalpy. See, EGE, I am just using this for electron gain enthalpy. Okay, so group 17 elements which are halogens, they have very high negative electron gain enthalpy because they can attain stable noble gas configuration by picking up an electron. And you see, because you see, for example, if you consider fluorine, it has an atomic number 9. So if it gains an electron, okay, then its configuration, you see there are 9 electron in it. If it gains one more electron, its electronic configuration will become 1s2, 2s2, then 2p6, so that there will be 10 electrons. This is actually the electronic configuration of neon, which is a noble gas. So, group 17 elements, halogens, have very high electron gain enthalpy because they can attain the stable noble gas configuration by picking up an electron. And depending on the element, the process of adding an electron to the atom can be exothermic or endothermic. See, for chlorine, the process is exothermic because energy is released during the electron addition. See, noble gases have large positive electron gain enthalpies because electron has to enter the next principal quantum level, leading to a very unstable electronic configuration. That is for neon. Neon, it is a noble gas. It has a very stable configuration. You know, neon, its atomic number is 10. So, electronic configuration will be 1s2, 2s2, 2p6. It is a very stable configuration. So, if we add one more electron to this neon, what happens? Its electronic configuration will become 1s2, 2s2, 2p6, 3s1. One more electron is added to neon. This is an unstable electronic configuration. Okay, so for neon, if we add one electron to neon, the electron gain enthalpy for that process will be plus 116 kilojoule per mole. This positive electron gain enthalpy indicates that energy is required to add an electron to this atom. That is, energy is absorbed and it is an endothermic process. See, electron gain enthalpies have large negative values toward the upper right of the periodic table preceding to noble gases. The electron gain enthalpy becomes more negative with increase in the atomic number across the period. The effective nuclear charge increases from left to right across a period, and it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. And electron gain enthalpy, it becomes less negative as we go down a group, because as we move down a group, atomic size increases, electronegativity decreases. Okay, atomic size increases as we go down a group, atomic size increases, electronegativity decreases, and the added electron will be farther from the nucleus. That is the general case. But you see the group 16 elements and their electron gain enthalpies. Oxygen, sulfur, selenium, tellurium and polonium group 16 elements are given here, and their electron gain enthalpies are also shown here. For oxygen it is minus 141 kilojoule per mole. For sulfur it is quite bigger than that, minus 200 kilojoule per mole. All other are actually in the decreasing order. 195, 190, 174 decreasing order. No. So here the electron gain enthalpy of oxygen, it is less negative than the succeeding element, which is sulfur, because electron gain enthalpy of oxygen is minus 141 kilojoule per mole. For sulfur it is minus 200 kilojoule per mole. So electron gain enthalpy of oxygen, it is less negative than the succeeding element, which is sulfur, because when an electron is added to the oxygen, see, oxygen has an atomic number 8, sulfur atomic number 16. So oxygen, its electronic configuration will be 1s2 2s2 2p4. Sulfur, it is 1s2 2s2 2p6 3s2 3p4. So the outermost shell is 2p shell here and 3p shell here for sulfur. And for oxygen, the outermost electrons are 4. It is the p orbital, so px, py, pz orbitals are there, no? So 2px, 2py, 2pz. According to Hund's rule, one electron will occupy each p orbital first, so 1, 1, 1, and the fourth electron will be filled in the first px orbital here. So this will be the the filling up of the the electrons in a 2p orbital for oxygen. And for sulfur it is 3p orbital, so 3px, 3py, 3pz. 4 electrons are there, so 1, 2, 3 and 4. This is filled as per the Hund's rule, which we have already discussed in our previous video. So here the electron gain enthalpy of oxygen is less negative than the succeeding element sulfur, because when an electron is added to the oxygen, the added electron goes to the smaller n is equal to 2 principal quantum level. Okay, when an electron is added to this, then that electron will go to this energy level. Okay, and the smaller n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level. Actually, there are 4 electrons already present in the 2p level. When one more electron is added, the repulsion between the electrons increases. For sulfur, the added electron will occupy the n is equal to, if we add one more electron to sulfur, it will occupy the 3py orbital here, that is p orbital. So for sulfur, the added electron it occupies the n is equal to 3 quantum level, which is a larger region of space and greater distance from the nucleus. So electron-electron repulsion is much less compared to this. That is why the electron gain enthalpy of oxygen, it is less negative than the succeeding element, which is sulfur. Okay, so in this video, we have discussed about the electron gain enthalpy. I hope it is clear to you. Thank you.